Welcome to this last lecture on the introduction to grant. That I want to do in these last few minutes with you is finish off the coverage of our soft information use and talk a little bit again about performance and revisit briefly the issue of how we can take into account the correlation of a noise, an issue that we brought up in one of the earlier lectures. So remember that what I'm doing here is I'm trying to take into account the actual noise behavior. This is something where I'd like you to think of, here's the signal to noise ratio. And here's, the signal that you might receive, say a BPSK, that's ranging between -1 and +1. And you can see, of course, as the signal to noise ratio goes up, the concentration around the actual transmitted symbol, say -1 or +1, is going up. So this is a heat map where you see cooler colors indicating lower probability density function values and warmer colors indicating higher ones. And of course, as the signal to noise ratio goes up, you can see that you get a more and more diffuse range. And actually, so your decision region, even though it's always to the left of 0, you would think it's a 0. To the right of it's a -1. To the right of 0, you would always think it's 1. If you're doing hard decision, your self-decision region would change quite a bit. I mentioned symbol reliability grant, which adds targeted guessing by having a single bit of quantized self-detection, which looks at just with that self-detection, looks at just whether a bit is basically had a very high reliability or not, and doesn't try to guess noise on the high reliability bits. I've mentioned ORB grant. ORB stands for Ordered Reliability Bits, which is an approximation of S grant. And in the last lecture, we went over S grant. So I mentioned earlier CRC aided list successive cancellation list decoding. What's happening there is that you have the soft information, so a continuous wave that comes in to be demodulated, and this floating point information that's going to identify the list of potential code words. Then what we have is that you create a list based on successive cancellation, where instead of decoding to a single code word, you decode to a list. And then you pick from that list by selecting which from the list actually pass a CRC, cyclic redundancy check. This is a proposed decoder. This proposed decoder was proposed by Tom Barty, was actually licensed by Samsung a couple years ago. What we do with grant is, if we have only hard information, if we only have the demodulated bit, demodulated symbol, then this is grant. If we have full float information, then this is S grant. And if we approximate it, we have ORB grant. Okay. I wanted to spend a little bit of time going over this picture. I mentioned many times that grant and its soft variants are adequate for low to moderate redundancy codes. This is what I mean. It doesn't necessarily mean that the code is short. You can see that I can go here to long codes. It doesn't necessarily mean that the rate of the code is low, it's high. You can see that here, of course, I can always do high rate codes, but I can go to actually fairly lowish rate codes. By the way, again, we're using a heat map here where cool colors indicate low probability, warm colors indicate high probability. This is probably a block error rate. And what you can see here is that, of course, lower rates correspond to somewhat lower block error rates. So think of this as being like a 10 to the minus 5 block error rate. Usually we'd like the block error rate in many applications to be around 10 to the minus 3. So think of this light green as being an acceptable region. Sometimes you can go 10 to the minus 2, sometimes you need 10 to the minus 4, 10 to the minus 3 is a good back of the envelope, a decent performance of block error rate. So with that in mind, what we have is that you can see that all of these rates and all of these block lengths, all of these code lengths are appropriate. But what happens, this is the signal to noise ratio. For hard detection, this would correspond to a probability of 10 to the minus 3 bit flip for the signal to noise ratio. And what you can see with overgrad is you can do all of these. The main point here is that the amount of redundancy in all of these points is moderate, okay? So again, it's not so much about rate, it's not about length, it's just really about the redundancy. I wanted to go back and look a little bit more at some of these issues around soft information. I showed you some curves indicating that the soft information as granted very well. And I told you that OR grant also does very well, but I haven't actually shown you that OR grant and S grant have very similar performance. So here you see, this is a CRC-aided polar code. Here you see grant. Here you see grant if you have just symbol reliability. Here you see the soft information with a list size of 16 in some of the previous figures I showed you, list size of 32. Again, still a very generous list size. And this is actually what happens if you do S grant or its approximation or grant. It does much better than the state of the art. What's interesting here is here SR grant with probably, this is basically how much we went with abandonment. So that's why you get this flat here. Now, one of the things I want to point out is that we're not doing this type of operation that you see over here. We're not first doing a list and then selecting using a CRC. All that we care about is to be able to check. A CA polar code is actually a linear code. So the kind of check that I showed you that you can do to verify that a syndrome is 0, you can do on a CA polar code in the same way that you could do on any other code, such as a BCH code. It doesn't matter. Just because it's a CRC-aided polar code doesn't mean I need to do a 2-step decoding. I can do a single-step decoding, okay? So I want to really emphasize this. I do not need to do a 2-step decoding. I can do a single-step decoding and do a single check of a linear relation in what was received. Okay. So we have these relations. And we observe that actually in some cases, and so by the way, here's a check that I was mentioning, the 1-step decoder with the CRC and the polar code and the interleaver all going together in a single matrix, and it's that single matrix that then leads to the check without the need to go through the intermediate step of doing a list. In some cases, even with hard information, with only hard information, we actually do better than the state-of-the-art soft decoder for CRC-aided polar codes, which is actually interesting. The strength of the decoder is such that sometimes even with only hard information, we can do better than with soft, okay? What's also interesting is that we can now compare using orb grand. Why do we use orb grand versus S grand, which I presented to you? It's because while S grand, has manageable complexity, still, it's a bit slow. It's good for actually getting results. And I would definitely say from now on, if you do any sort of comparison of a decoder, you should always check it with SGRAND, because now you do have a true ML decoder. It's, if you will, the gold standard. There's no excuse for not plotting the gold standard. Then, for actually running real time, we think SGRAND is a bit slow, or GRAND, on the other hand, is quite fast. So you can get results much more readily with OrgGrand. Now you can see here is the RLC and the CA polar basically do about the same, while this RLC, of course, as we mentioned before, because it's unstructured, you can have at any code length, you can have at any rate, you can pick however you want. Just a few more results. Again, here, this is with hard decoding, state-of-the-art soft decoding for CA polar code. Now what you can see is that RLC and CA polar, this is not a polar here, and SGRAND, all of these do the same on CA polar codes or on RLCs, whether you use SGRAND or ORGRAND, it's all the same. Basically, almost all codes are good. Okay. And the RLC and the CASCL basically do the same. The complexity of the codebook search is actually quite low. Again, remember that I probably want to be at around 10 to the minus 3, which means that I'm calling this X grand because it doesn't matter whether it's ORB grand or S grand. For all intents and purposes, they do the same. Suppose then I would be at like a little below 5. What you can see here, a little below 5, is that the number of queries is somewhere around 1,000, which is not very high. That's not a lot of operations. And you can also see, as we've mentioned before, the effect of the increase in signal to noise ratio in decreasing complexity. So here, if suppose I want to be at 10 to minus 4, which would mean I'd be at around 5 point something, the number of queries is around 100, given that the code length is itself only about 100. We really can't be hoping for a lower complexity in terms of number of queries. So, there's just something to bear in mind. And then my rate goes down a little bit and my length goes down a little bit. My number of queries is very low, really order 1. We're talking about 5, 10 queries, 5 queries or so. When we talk about a single decoder, it really is a single decoder. You can see here, if I fix different code lengths, you can do all of these rates. All of these rates are done with a single decoder. One of the things to bear in mind is that in modern systems, not only is there a different chip for different codes, in some cases, you have a different piece of hardware for different rates of the codes. So basically, your chip starts looking like a Swiss Army knife, trying to decode all kinds of codes at all kinds of rates. And here you have a single chip. Soft detection, again, polar codes by themselves without the CRC don't do well. They do, CRCs do well, polar codes with CRCs do well. Pretty much everything does well except for, I would say, raw polar codes. The last thing I wanted to bring up, because it was mentioned at the beginning of the class, is this issue of interleaving and of memory in the channel. This channel trace that you see here is a bit error frequency. So think of this as the bit flip probability for different bits and different positions in a frame. Okay, this is before interleaving. You can see there's quite a bit of memory, and you can see that towards the end of the frame, things are getting a little more flaky. If you think all the way back to the first lecture on GRAND, remember that when we were guessing where a noise may have occurred, I mentioned to you that we were going to guess the last bit, because often it was towards the end of the frame that things went badly. Same thing that you can see here, you know, towards the end of the frame, your clock sync is getting so-so. You know, it's not that because there's more noise, just because things on your system are getting a little bit more flaky. And so you get more, tend to get more bursty errors. And what you see here, you know, like I said, because of time slippage and other effects, as here is after interleaving, it looks like it's uniform throughout. If I actually take into account using a Markov order, that's what MO stands for, and encourage you to read our paper with a certain way and keep the bursts and ditch the interleavers. So the title says it all, keep the bursts and ditch the interleavers. You can see that as a system becomes, that if you have, say, a BCH code with a Burley-Camp Massey decoder, which is very good in the case of uniform noise, and that's what you get with a binary symmetric channel. It's this turquoise curve here. If you try to apply Burley-Camp Massey as you get Markov with greater memory, and so you should think of this G level here as indicating different levels of memory. So more bursty in this direction, more bursty. So basically, as it becomes more bursty, the channel has worse and worse behavior. Except if the channel is so bursty that it starts to be that the mixing time of the channel is of the order of the length of the code, which is happening in this line over here. Actually, what you see is that with the Markov order decoder, because we can make use of the memory in the channel to guess that there will be a clumping of errors, you can guess the noise more readily. Again, an effect that had been hinted at the beginning of the class, but that you can see more clearly here. Okay, so basically what you see here is that, you know, for a bursty channel, you're getting about a power factor, you get over 3 dB, so over in EB over N0, which is energy per bit, over the N0 is the noise spectral density in a white Gaussian noise we're assuming here. But also you're getting a delay factor actually of about 100. So remember that we talked about ultra reliable low latency communications. Having interleavers goes very much against ultra reliable low latency communications. Being able to ditch the interleavers is benefiting us from an EB over N0 from an energy perspective. It's also really benefiting us massively from a delay perspective. Okay. Here with CA polar codes, we see a power factor of over 4, and again, a delay factor of 100. So very, very strong benefits from using GRAND by taking into account the statistical behavior of the noise. So with that, I wish to conclude. Thank you for following the course. I want you to think really again about the philosophy of GRAND, which is to stop making the engineering look like the math, make the math look like the engineering. For those of you who watched the lecture on the more mathematical science, you can see the math can be a little different, but you actually don't need to know the math of that shows, you know, the detailed error exponents, success exponents, and the really fine-grained behavior of the algorithm. The algorithm itself, as you saw, is super, super simple. You can't really get a more simple algorithm than GRAND. So, you know, if you just take away the GRAND algorithm, I'll actually be very pleased as that being an outcome of this course. But basically, you know, you don't need to interleave. Don't worry so much about capacity. Just get the best read you can. The codes that are being used right now that are touted as capacity achieving, and they maybe are really working way below capacity in the systems that we have, right? So, you know, the LDPCs are like working usually much, much below capacity. So, you're not really using them as capacity achieving. And don't fight noise correlation, use it. Don't worry so much about the code. Pretty much all codes are good. Okay, some codes might mess up, be not so good like this, but pretty much all codes are good. CRCs, the humble CRC is a great code, and it's super, super easy to check whether something is a code word or not. CRCs are built to be very easy to check. So, I hope that you've enjoyed this and just have fun and play with the algorithm.